Okay, guys, I think you're able to hear me. Oh, not there. So only
Yes,
Benisha
sir.
and Rohan, only two of you are there. Okay, so we'll wait for 2 more minutes. Let people join and we'll see.
Okay, sir.
Three of you, Pranav joined. Okay, Rahul came. So 1 more minute, we'll wait, guys. Let people join. So, guys, how was Diwali? Was it okay? You all celebrated nicely?
It was okay, sir.
Ah. So, anybody followed the green Diwali? No crackers? Anybody did that?
I did, sir.
Okay, that could. So, but because I didn't do it. See, according to me, it's see, you have all 365 days factories running. You don't stop your vehicles. Like the amount of pollution those they create, the in one day, how much? Like it's gonna happen in once a year, right? So like it's been happening for the past I don't know thousands of years. Diwali, right? So I don't think this makes up like this will actually contribute so much to the pollution as such, right? So yeah, like if you're not able to stop so many other things, you don't stop the sentiments of people. Like that's what I believe in. Anyways, it's good. It's good that if you didn't what is that bus crackers, it's actually nice in one way. Right? Okay, I think we are good to go. We'll start, people. Right. So let me flip my screen. Okay. So guys, let me share my screen. Okay, so I think you're able to see my screen. Where's my Okay, hope you remember. This is what we have been seeing. If you look at the screen, you can actually remember what you have been seeing. Okay, fine. So what we have been seeing is about entropy, right? So I think when I first introduced entropy, I told you what is it. So it's the measure of how much randomness which is there in the system, right? So when we went to the mathematical definition of what is that entropy delta S. That is I told you it is equal to Q reversible divided by T, right? And we told why Q is in the numerator, why temperature is the denominator, and what is the significance of writing Q reversible there, right, and not just Q, right? Anyway, anybody wants to comment? Why is that I put a reversible there, Q reversible? Why is it like that? I gave you a reason for this. Does anybody remember?
It's a constant path function, sir.
Correct. So I want entropy to be a state function. I don't want it to be a path function, right? So because path functions are always difficult to deal with, just like your work or heat, right? They are a little difficult to deal with. But when I convert it into a state function, that is, if it's going to depend only on the initial and final states, it is always easier. That's why it's easier to work with a what is that, delta H, delta E. All these are state functions. So that's why I now what I do, I just make the path constant, saying that it is going to be only reversible path. There's no other pathway. So by that it becomes a path function. So yes, that was the thing. And then I think last class we went on to see what the second law of thermodynamics, right? See, second law of thermodynamics is going to talk about the spontaneity of a process, right? We know what do you mean by a spontaneous process, right? A spontaneous process is one which will happen on its own. We don't have to do anything for the process to happen, right? So any such process is what is called as spontaneous, right? So what second law said, right? The second law talks about the direction of the spontaneous process, right? So it said that the direction of the spontaneous process should be in such a way that the entropy delta as universe is always to be greater than zero, or say the entropy of the universe is always increasing, right? Now I said we have to be very, very careful, right? We are talking about the entropy of the universe that is equal to entropy of the system plus that of the surroundings, right? So you should not be, if you just calculate the entropy of the system alone and you see that it is less than zero, that doesn't mean that it is going to be a non-spontaneous process, right? You have to calculate for the system, you have to calculate for the surroundings, sum them up, then you have to look at the delta as universe value. Now if it is less than zero, yes, it is non-spontaneous, and if it is greater than zero, it is spontaneous, right? So that is what we said about this thing, and we went on to prove it also, right? We took melting process, I think we took freezing process, then we proved it, then we took boiling of water, we again proved it, right? Saying that delta S universe is going to be greater than zero for a spontaneous process, right? So we proved it, right? Okay. Now what we saw till that is, yes, it is one form of second law. I told you there are different statements of second law of thermodynamics given by different scientists, right? So this particular thing which we saw is for the direction of a spontaneous process, right? And there are other ways of looking at it also. So we'll see what are the other statements of second law, right? So we continue. So the second law, the next statement, right? So next statement we'll be able to speak in terms of engines, right? So in chemistry, yes, they have less significance. I mean, the chemistry part of thermodynamics, it doesn't, what to say, it is not much important, but still, like you have to learn, you have to know it, right? And I mean, eventually you will like this engines part. The engine part of second law of thermodynamics is little important when you come to physics, but still, we'll learn it now, right? Fine. First, act on the statement, people. And then actually, it's a very interesting statement. Right? Just go for it. I'll tell you the statement now. Please take it down. There is no engine, or there cannot be any engine. There cannot be any engine which converts heat to 100% work. There cannot be any engine which converts heat to 100% work. Okay, that's a very simple statement, right? So we'll analyze this. First of all, we need to know what an engine does, right? Then we'll be able to appreciate the statement, right? See, we know what engine basically what does it do? So basically, for example, we'll take the known examples. We'll take a car engine or say your bike engines, right? So what do they do? So basically, you have the fuel, right? Now the fuel is getting burnt inside the, like, that is not a part of the system, but still I'm just telling where the fuel is the energy source, right? Okay, so you have a fuel injector system. Like you will study about it when you go for maybe the first year college. Like it's irrespective of what department you take. I mean, E&I or ECE or mechanical or CSE or whatever it is, you will be studying about engines if in the first year. That's the these are the basics you have to know. Anyways, so what I'm telling is, so there's going to be fuel, right? So that fuel is going to get burnt, right? Now there is a lot of heat energy produced during that burning of the fuel, right? Now that heat energy is given to the engine. Okay, that heat energy produced by burning of the fuel is given to the engine, right? And the engine uses that heat energy, right? And it does some work, as simple as that. And work in the sense it makes your it makes your what is it, the vehicle move, or any other kind of, say it makes a motor rotate, something like that, some generator, something like that, right? So basically, the what is the role of the engine? Any engine for that matter, any engine basically converts heat to work. As simple as that, right? Any engine for that matter, the heat is the input, right? And work is the output, right? Hope you understand. It's very simple. Like again, there are a lot of complicated things will happen inside a system, an engine, right? But we are not interested in all that. We just want to know the outline, the gist of it, right? The gist of it is that any engine will be able to convert heat to work. Now the question is, right? Now if you look at the statement, now if you look at the second law of thermodynamics statement, it says there is no engine, there cannot be any engine which can convert heat to 100% work. Now, what do you mean by that? Say, for example, if I give 100 joules of heat to the engine, okay, I give 100 joules of heat to the engine, right? Now what happens now if I expect that this all this 100 joules of heat will be converted to work? No, that is not the case, right? Maybe out of 100, maybe say only 70 joules can be converted to work, right? Now what happened to the rest 30 joules? Now rest 30 joules is my heat loss, right? Now you would have seen this is a common thing which we see, right? Anything which does work, anything, literally anything which does work, there will always be heat loss. And you can see it in the bikes also, you can see it in the cars also. Say now whenever you run the car, whenever you run the bike, what happens? The vehicle becomes hot, isn't the silencer becomes hot, the vehicle becomes hot, right? So this is exactly what is happening in the engine, right? So there is some amount of heat energy you give to the engine. It converts some of it, like say in 100 joules, 70 of it is converted to work. But what happened to the rest 30 joules? They are just going to go to the surroundings as heat loss. Okay, so this is what my second law says. That means you cannot even imagine of converting all this 100 joules of work into 100 joules of heat into work. It is impossible. That's what my law says, right? And I mean, and it turns out to be true. You cannot do it. It's impossible. You if you're gonna do that, I mean, if you're gonna do it, you are going to violate the law of nature. See, this is not something. This second law is not something which is experimental, right? It is what we observe in nature, right? So if you're going to do that, you're going to go against nature. Like, I'm trying to say that it's impossible to do that. Okay, right? Now if I want to give you any other example, like even if you take the smallest of things which we do as human beings, right? Say for example, you take your hands and say you clap, right? Now I don't know whether you will realize it, but actually you did some work here, isn't it? Your body spent some energy in doing this work of clapping, right? So if you just feel, I don't know whether if you can feel it, actually your hands would have become hotter, right? So you can try if you want, like maybe, like definitely that your hands would have become hotter after you clapped, because what happened? You did some work, right? So whenever you do some work, heat is an unavoidable consequence. There'll always be heat loss, irrespective of whatever work you do, right? Okay. Now say another thing, like when you say workout, when you go for gyms or when you go for jogging or when you play, whatever it is, right? Why is it that your body is getting why is it that the body is sweating? We all know the reason. This is the reason, because whenever you do work, your body becomes hot. Because any engine, our body is also an engine only, because we how do we connect, okay, how do we correlate human beings with engines, if you ask me? right? So engines, what they do, so basically there is a fuel, it is getting burnt, and the heat produced is getting converted to work. Same happens here. We take food, the digestion is actually a burning process. It burns the food, right? So there we get some amount of heat energy, and that energy again converted to work. So that's exactly what an engine is also doing, right? So what I'm telling is, if you play or do any kind of workout, right? So why do you sweat? Is because whenever you do work, heat loss is there. Your body becomes hot. So the is just to reduce the body temperature, right? Okay. Now, sir, is there any way that I'll be able to violate this? Right? The whatever the statement which we saw now, right? No engine can convert heat into 100% work. Can I violate it? Right? So the answer, technically speaking, there is there is one more what to say, one more different version of this statement, second law, right? Which says, you can, if you want, you can take it down. It says that you can convert. Say if I have 100 joules of heat, right? If you have 100 joules of heat, you can convert into 100 joules of work if and only if you do the particular process at 0 Kelvin, right? So if you look at it, right? So what there is one more version of second law which says, yes, it is possible, right? You can convert 100 joules of heat into 100 joules of work. I mean, how much ever heat you have, you can convert it to work, 100% efficiency, right? But the temperature should be 0 Kelvin, or 0 Kelvin, I know it is equal to minus 273 degrees Celsius, right? But again, right? How can there can be one statement and there can be another statement which violates each other? Impossible, right? That's not how science works, right? So what do you mean by this is that you will not be able to reach this particular temperature, 0 Kelvin or minus 273. Till now, we have not reached, right? So, or in other words, you can say that one more form of second law, I can say that it is going to be, I mean, there is no way that anybody can reach the temperature of 0 Kelvin. It's impossible, right? So either way, what you have to understand is conversion of heat to 100% work is impossible. It is possible when I have 0 Kelvin, but again, 0 Kelvin cannot be reached, right? So we have even reached minus 270, minus 271, but minus 273.15 is the exact temperature that we have not, like, even with the so much sophisticated instruments, the biggest of laboratories, they, I mean, we will not be able to do. Again, if we do it, that means we are violating the law of nature, right? Fine, maybe not on this earth, right? So yeah, maybe in other parallel universe, if you believe in that, right? So maybe there it is possible. Okay, right? So that's about the engines. Okay, so this is about the one of the ways, right? Say this 0 Kelvin is about one of the ways of doing this 100% efficiency thing, right? Now there is one more way also we can do it. But again, obviously, I'm going. If I tell you that there is a way, again, that way is again going to be unachievable, right? So what is that way, right? So if you can do the process, so this 100 joules of heat to 100 joules of work, if you do the process 100% reversibly, right? We know what is an 100% reversible process, right? Infinitely slow process, right? Infinitely slow. Say, this is how they say, right? For example, if you take your bike, right? Now, if you want to give good mileage, you know what is the mileage, right? So basically, for the amount of petrol you put, how much distance it covers, that is what is mileage, right? So generally, what happens if you're going to drive your bike a little slower, not like rash driving, right? Obviously, when you do rash driving, the mileage will be very less. The performance might be very high, right? But the mileage, the efficiency is going to be very, very less if you're gonna drive, if you're gonna drive your bike very fast, right? But the same thing, you maintain some constant good speed, but not so much, right? So eventually, for 1 liter of petrol, so definitely you will see that the mileage has been increased, right? So I think you're able to understand what I'm trying to say. If you are going to do the process as slowly as possible, in the sense, if you're gonna do it only an infinite amount of time, like basically you want to move from one corner of the room to the other corner of the room, basically you're doing some work, right? One corner of the room to the other corner of the room, you're going to move, right? So but the thing is, but you want to convert all the heat energy into work, 100% efficiency. So what you have to do, you have to move so slowly that you will eventually not reach there at all. But I mean, if you reach there, like, I don't know, like, so basically we are telling that you have to reach only an infinite amount of time. But again, if you look at in reality, right, can we reach an infinite amount of time irrespective of however slowly you go, right? Irrespective of however slowly you go, eventually you will reach that point. So you will not be able to do a process for an infinite amount of time. But if you are able to do that, right, if you're able to do it in infinite amount of time, so yes, this particular thing is possible, right? 100% efficiency of converting heat to work is possible. So again, there are two conditions in which you will be able to violate the second law. First one, 0 Kelvin, the process should be done at 0 Kelvin, but again, it cannot be reached. And or when you do the process 100% reversibly, but again, that is not practically possible. You will eventually finish the process in some finite amount of time, right? So this is what is your second law, I mean, in terms of your engines. Any questions, people?
Could you repeat the second point statement alone, sir? Like that process 100% reversible point.
Yeah, so what I'm telling is, when you want to convert heat into 100% work, right? If you do the process 100% reverse, we know what is the reversible process, right? The reversible
Yes, sir.
process is one which is going to happen infinitely slow, very slow process, right? So if I want to say 100% reversible, what do you mean by 100% reversible? 100% reversible means as slowly as possible, or in the perfect words, if I have to put, the amount of time taken to complete that particular process is infinity, right? The process will get completed only in infinite amount of time. That's a 100% reversible process. If you can do the process that slowly, so yes, 100% conversion of heat to work is possible. That's what I'm saying. Understood?
Okay, sir. Understood, sir.
Any other questions, people? Any other questions? Anything in the chat? No? Okay, now let me ask you this question. You have a dead body, okay? We all know dead bodies, right? So what do you think? The dead bodies have, okay, I am saying that dead bodies have zero entropy. True or false? Just put it in the chat box if you want to put, or you can just unmute yourself and tell me. The question is that for a dead body, the entropy is zero. True or false? Okay, Rahul says true. Okay, Shruti says true. Pranav says true.
So the question was for a dead body, sir.
Yeah, for a dead body, the entropy is zero. True or false? Okay, Venisha objects. She says false. What about others? Okay, Abhishek says true.
1 minute,
What about
sir.
you, Rohan?
Thinking, sir.
Sorry?
I'm thinking, sir. Just a minute.
Okay, fine. Think. Yeah. I think almost everybody answered, right? So I think, Rohan, you have to give your statement in the sense, either it's true or false. What do you think?
Sir, what can I say the question again, sir?
Sorry?
Can you say the question again, sir?
I'm telling, for a dead body, the entropy is zero. True or false? Okay, Rahul wants to change his statement. He says false. Okay, fine. I think that is Bhavadarini, keyboard lovers. Is that it? Correct? Is the Oh, it's Mithun. Okay, fine. Oh, you didn't rename. No problem. Okay, so yeah, so this, whatever the question I asked you, right, is actually one of the very strongest debates we can have in science, right? So it can be regarded as true, it can be regarded as false, depends on how you look at it, right? Okay, fine. So if like the logical answer would be true, right? Basically, because nothing is happening, there is nothing moving no moving in the body. It's just some mass just lying on the floor, right? So yeah, we are bound to think, yes, entropy, there is nothing happening there, right? Yeah, it's zero. I mean, the entropy is zero, right? But I would say you have to think in this angle also. For example, say when you're going to preserve the body, in the sense when you're going to keep it in an ice box or something, or when you embalm it, you know what is embalming, right? So basically, you have formaldehyde, HCHO, right? So you inject HCHO into the body will be preserved for a longer amount of time. So yeah, so in those conditions, definitely, right? Whenever the body does nothing, but it just stays, right? Yes, the entropy is zero. We can say that, right? But if you're not going to preserve the body, say for example, there was a murder in the forest, right? And the police department found out about the murder only after say 1 month, and they find the body. So obviously they will find the body in a decomposed state. It will not be preserved, right? At that time, definitely I cannot say that the entropy is zero, isn't it? Why? Because the microorganisms are acting on it. Something is happening to the body. The mass is changing. Something, all the things are changing, right? So definitely at that time, I will not be able to tell that the entropy of the body is zero. So we'll not be able to conclude like that. So this is one of the very strongest debates. Still, scientists are debating for a dead body whether I should consider the entropy as zero or not. That's why even I asked you this question. But again, all whatever the answer it is, whether it's true or false, it depends on how you look at it. Okay, right? So that was a good question, isn't it? Right. So you can also ponder over it. You can also look into videos. You can also look at Google, ask Google what it says. Even Google will be little confused, right? So, anyways, so that's what I wanted to ask, right? So yeah, any other questions you want to ask? Anything else?
No,
Okay,
sir.
okay, so I suppose no. Cool, right? Right. So we continue, right? So that is about your second law. Okay, fine. Now I'll give you a very small this thing, small mathematics regarding engines, right? Not like how engine works, but to calculate the efficiency of the engine, right? So I think it should be there in your books. We'll see that. Okay, right. So if you look at the overall working of the engine, right? So this is how it is going to look, right? So I have something called as a source, right? Source in the sense energy source, right? So obviously I told you the fuel is your source. The fuel is getting basically wherever the heat energy is coming from, that's the source, right? Now this heat energy will be given to your part called as engine, right? And obviously, for some amount of, say, I give some Q, right? The Q is the heat energy I give to the system, in the sense engine, right? So this will convert some amount of this heat into work, W, right? And obviously, we know according to the second law, not all that is Q is not equal to W. Right? Obviously, there's going to be some heat loss present. So that heat which is lost is given to something called as a heat sink, we call it, right? Source sink, right? So this is some Q1, I call it, right? So this is, so how will now if I want to if I want to do the energy conservation, how will I write the equation? It's very simple. This is the total amount of energy given, right? Total energy given should be equal to the total amount of energy in the whatever the process, right? So I can write Q is equal to W plus Q1, right? So what my second law says is that this particular value can never ever be zero, right? That's what it says. Okay, so that's we already saw, right? Now how do we calculate what is the efficiency of an engine? Okay, before we see that, we'll see
Sir,
something about source, right? Now please understand, source should be at very high temperature, right? The
excuse me,
source
sir.
should, yeah.
Sir, I got disconnected in the start when you're explaining this. Could you explain the starting of this
Yeah,
alone?
no issues, no problem. So what I'm saying is that this is the overall say the parts of the engine, in the sense the overall how is it able to convert into work. So I have something called as a source in the sense, say if I can take the example of your petrol, or say the fuel injectors, like where the fuel is getting burnt, the heat energy wherever the source is coming from, that's my source. And that there'll be some amount of heat energy that is given to the engine, right? And we know some amount of this heat is converted to work, and I know Q is not equal to W because you will be violating second law. So obviously there will be some amount of heat loss from the engine, and that will be given to the sink. Okay, that's
What
the
is the
overall part. And
sink, sir?
this particular equation which we wrote is just the energy conservation equation. Total energy given should be equal to sum of these two. Like whatever energy you give should be equal to the total work done plus the amount of heat loss. So that's how I write the statement. And I told you this Q1 cannot be zero. If it's zero, you'll be violating second law. That's what I told.
So I have a doubt.
Yeah.
So what is the sink actually, sir?
One second, Kanna. Tell me.
What is the sink actually, sir? The sink.
I'll tell you. We are speaking about the source and sink. Wait. I'll tell you the
Okay,
one.
sir.
Right? Okay. So when I talk about the source, people, right? So source is one which should be at a very high temperature. Okay. Now, why should I have it at very high temperature? Is because when you want to do that, when you want to have the efficiency of the engine to be very high, right? You can see it mathematically also in some while. So you need to have very high temperature for the source, right? Now, one more reason that why I need to have it a high temperature is that the thing is, if it's an ideal source, a perfect source, even though it gives some amount of heat, Q is given to the engine, the temperature, whatever I have here, say it is some T1, this value should not change, right? Even though it is going to give some amount of heat, right? The temperature value of the source should not change. Okay, right? Fine. Next, when I go for engine wheel, we know what like, it is a complicated thing, right? So there's something called as Carnot engine. You will be studying about it in your physics in depth, right? So don't worry, there is going to be compressions, adiabatic expansions, isothermal compression, something will happen, right, inside the engine. So your physics sir will talk about it. We don't have to talk about it, right? Coming back to sink, right? Now, obviously, what is the role of sink here? Right, so please understand that there's always going to be some heat loss from the engine, right, and that has to be given to something, right? You cannot see if it's a normal if it's going to be very less amount of heat like your vehicles, like what we do on your motorbikes. What is the sink is basically the atmosphere. There is nothing, right? But if you go to power plants where enormous amount of heat is produced, right? So in that case, they will not be directly, they cannot give it to the atmosphere because that will pollute or increase the temperature of the atmosphere. So what they do is they have a separate, it's like, just like source, right? It's just like source, just that here also I have high temperature only, right? Say it's T2, but T2 is less than T1. That is, the source is always at a higher temperature. So that's what you need to know, right? So again, why I have higher temperature? Again, because I need to have what is that? A higher efficiency. I think it's lower temperature. But anyways, so the thing is, it can be either very high or very low temperatures. Now, why do I have this? There's the same reason. Even though the sink is getting some amount of heat, right? The temperature value should not change. That's the reason. Okay, so basically sink is a place where you give an amount of heat, and sometimes you can even have a feedback system, in the sense you're giving some Q, right? So this can again be given to the source. The amount of heat which is produced, which is given here, the Q1 can again be given to the heat, to the source, right? So again, by this you increase the efficiency of the engine, in the sense not so much amount of heat is actually lost to the surroundings, obviously, right? So anyways, this is the overall parts of the engine: source, engine, and your sink. Okay, now how do I calculate the efficiency? Right, now it's very simple. Efficiency is given by the letter eta, right? This is a Greek letter. Eta is equal to it's pretty simple, right? How much work you're producing, right? How much work you're producing to how much amount of heat is given to you, right? So the amount of work W divided by Q is what is my efficiency. And if they ask you in terms of percentage, you have to multiply the numerator by 100. That alone you take care, right? So work W, the work W which is getting produced due to the amount of heat, divided by what is the amount of you actually gave, into 100 will give you the percentage efficiency. But if you don't want to multiply this by 100, you'll get it in the form of a fraction. Obviously, this value is lesser, this value is always greater. According to second law, there'll always be some heat loss, right? And how can I write the work? I can write the work as Q minus Q1. From this statement, you can see, right? How will I write W? W will be equal to Q minus Q1 divided by Q, something like that, right? Now, this statement, like this particular mathematical form is going to help me convert this particular, what is that, efficiency in terms of temperature also, right? So if you look at it in the form of temperature, actually, or you can do one more thing. If you can take, if you separate the terms Q by Q minus Q1 by Q, so how can I write this? I can write it as 1 minus Q1 divided by Q. So no, this is not W, I'm sorry. This is my efficiency, right? So what I did, I just separated the terms Q by Q minus Q1 by Q, right? So what will happen now? I'll get eta to be equal to 1 minus Q1 divided by Q, right? Or if I speak in terms of your temperature, like I know Q is directly proportional to temperature, is it not? So instead of speaking in terms of your Q, I can even speak in terms of temperature. Now that how will I do? I can write eta as 1 minus, so the Q is coming from source, right? I mean, I can write it as T2 minus T1. So where, sorry, what is this? Okay, if we go back to that previous page, so if you go back to the previous page, you can see Q1 is here. Oh wait, so Q1 is here, right? So basically, it's going to the sink, and sink is at a temperature of T2. I told you this is at T2, right? So you Q1, T2, you can connect, and obviously, where is the what is Q? Q is coming from the source, right? There the temperature is T1. So instead of writing it as 1 minus Q1 by Q, which is coming, this is the source, this is the sink, I can write it as amount of temperatures also. That's what we did in this page. Oops, sorry. Right. So I can even write it in terms of temperature. 1 minus T2 by T, right? So all these formulas you can remember, or it's pretty logical to remember this also, right? If you just remember that eta is nothing but W by Q, and eventually you know how to write W. If you know how to write W, separate the terms, right? And then you end up in this statement. First you end up in terms of Q, then you can convert it in terms of temperature. And if they ask you in terms of percentage, just multiply this by 100. As simple as that. Okay, so that is about the efficiency of the engine. And that is overall about the second law, which speaks in terms of your engine performances, right? Okay, fine. Now this is about the second law, right? Now I'm going to introduce you to a very, like say, another term, right? So people, we are talking about the spontaneity, right? We are speaking about the spontaneity, and we said that for a spontaneous process, delta S universe should be greater than 0, right? So what happens is, if you're going to take the entropy as the criteria, if you're going to take entropy as the criteria for spontaneity, for spontaneous process, the problem is every time I have to calculate the entropy of the universe. In the sense, I have to do a double time calculation. In the sense, I have to calculate the entropy change for the system, and you have to calculate the entropy change for the surroundings, right? So obviously, you have to do a double time calculation, right? So that's actually a little disadvantageous. Okay, so to overcome this this thing, so what scientists did is that they introduced a new thermodynamic term. Again, repeat, right? So if you want to talk in terms for a spontaneous process, you always speak in terms of entropy change of the universe. And we say that for a spontaneous process, the delta S universe should be greater than 0. Right now, this is little disadvantageous, is because I have to do the calculation 2 times. I have to calculate it for the system, I have to calculate for the surroundings, sum them up, then I have to look whether the process is spontaneous or not, right? So what happened is, to overcome this particular difficulty, that is the doing so much calculation, what scientists did is that scientists took what is that? Scientists took, not took, they created another thermodynamic quantity. Okay, now that quantity helped me not do the calculation for the universe, but if I just calculate for the system alone, right, and if I look at the value, it tells me whether the particular process is spontaneous or not, right? So basically for delta S, you have to calculate both for the system and the surroundings. I'm going to give you another term, another thermodynamic, just like enthalpy, entropy, internal energy, all these things. There is one more term, right? So of that, if you calculate, right, now that you are going to calculate only for the system. That's the best thing about it. You don't have to calculate for the surroundings also. You just calculate that particular thing for the system alone. And there is again a way, there is again a criteria, right? If that particular value is this much or greater than this or less than this, then we say that that is a spontaneous process. Okay, so what is the thermodynamic quantity, right? The thermodynamic quantity is what is my G, right? So G, full form, it's Gibbs free energy, right? It's called Gibbs free energy, right? Now, how do I define it? Okay, now people, if you look at the first law of thermodynamics, I have say delta E is equal to Q plus W, right? So what you understand from, like, why did I write the statement now is because when you looked at entropy, we looked at the Q value, is it not? Right? When you looked at the entropy, right, you looked at the Q value, Q by T, which you put. I mean, if it's going to be a reversible process, right? Exactly, you took Q reversible, right? But if I want to talk in terms of W, right? So basically, the Gibbs free energy talks in terms of the work done. Okay, Gibbs free energy talks in terms of the work done. Right now, how will I be able to define Gibbs free energy? I will tell that it is the what to say, useful work in a reversible process. Okay, right? It is a useful work which can be extracted from a reversible process. As simple as that. Okay. So, anyways, the definition of Gibbs free energy. I would say the English definition of Gibbs free energy is not that important, but the mathematical definition is very, very important. Okay, so if you want to ponder about it, we can ponder about it, but again, it's how, what exactly is this is beyond the scope of your 11th class. Okay, so if someone asks you what is G, what is Gibbs free energy, just tell them that in a reversible process, what is the amount of useful work which can be extracted? That is what is called as your Gibbs free energy, right? So again, we will not be able to, just like all the other thermodynamic properties, we will not be able to find the absolute value of G. What I will be able to find out is my delta G, the change in Gibbs free energy. Okay, fine. So before we see this, we'll just see the mathematical definition of Gibbs free energy, right? And guys, till now, right, we have seen so many properties. The most important thermodynamic term for us is going to be this G. Okay, it's very, 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 very important. Okay, you will be able to appreciate this when you look for other chapters, because this is not the only chapter you'll be using it. You'll be using it in equilibrium. Next chapter, you will be using it in so many times, kinetics, chemical kinetics in 12th class, even in certain chemical reactions, in the sense in organic reactions, you will look at this, right? So it's the most important thermodynamic term, Gibbs free energy. Okay, fine. So how do I mathematically define it? This is how I mathematically define it. G, Gibbs free energy, is equal to H minus Ts. Very, very simple equation, where H is the enthalpy, T is the temperature in Kelvin, S is the entropy. Okay, H is the enthalpy, T is the temperature, S is the entropy. But again, we are not going to deal with this, because I told you that the absolute value, obviously none of the absolute value in this, nothing absolute value can be found out. So if I write it in terms of delta, right, now this is how I write it. Delta G is equal to del H minus T del S. Very, very, very simple. And obviously this delta is you're calculating for the system. This is also for the system only. This is also for the system. Okay, so as I told you, you don't have to worry about the universe's value anymore. So if we just calculate the entropy of system, right, and obviously that can be used for calculating the delta G of the system itself. So you don't have to worry about the universe's value anymore, right? So now what is the condition? Right now we started all these things, right, to determine what is the condition for a spontaneous process. We don't want to calculate it for system and surroundings and then calculate so many stuffs. So that's why we went for this delta G, right? So this delta G is also going to tell me the value of delta G is going to tell me whether the process is going to be a spontaneous process or not, right? Now what is the condition for a spontaneous process? Delta G should be less than 0. Very, 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 very important statement. Okay, for a spontaneous process, delta G, that is the change in Gibbs free energy, should be a negative value. Okay, now it's exactly opposite of entropy, isn't it? Now entropy of the universe, we said that should be greater than 0. Now we are telling the delta G of the system, right, should be lesser than 0 for the process to be spontaneous. Okay, so if they give you some positive values and negative values and ask you which of them are more or less spontaneous, more and more negative value you have, more and more is spontaneity, and more positive you have, positive value you have, more and more will be the non-spontaneous process. I mean, non-spontaneity, I would say. Okay, so this you are going to remember for the rest of your life, right? Spontaneous processes, delta G is going to be less than 0. Like if you're gonna take some BSc chemistry, or if you're gonna even if you're gonna any field of science you go, right? This actually is a very, very important thing. Delta G of the system for a spontaneous process should be less than 0. Okay, right? Now how can I make sure that the delta G is less than 0? Depends on the value of delta H, depends on the value of delta S also. Is it not? The overall thing is that I should have the delta G to be less than 0. So accordingly, you need to have a value, right? Say for example, if you say that the delta H value is negative, right, and this value is also negative, for example, right? If say I say the delta H value is negative, delta S value is negative, right? So obviously this is negative, and I have a minus sign here. In the sense I have a minus sign here, and this minus becomes positive, right? So what should I say now? Obviously, I want the delta should be less than 0. That means this negative value should be very, very, very high. Only then the process is 0. Or in other words, I can say that the temperature should be very less. Hope you're able to understand, right? So if at all I have this particular thing to be negative and this particular thing to be negative, T delta S term will become positive, right? But I want this value to be greater than this value because I want the overall thing to be negative. So what should be, what is the thing? I can say that this particular process, what you're speaking about, will be spontaneous at very, very less temperatures. So that's what you need to understand, right? So like this, I'll be able to predict whether the reaction responded at lower temperatures or higher temperatures or at all temperatures, right? So can you tell me what is the what should be the how should be the value of delta H and delta S for the process to be spontaneous at all temperatures? You tell me. I'll repeat the question. What I'm asking is, how should be the value of delta H and how should be the value of delta S so that the process is spontaneous at all temperatures? How should be the value?
Delta H should be smaller than delta S.
No, I'm asking whether they be positive or negative, something like that.
So delta H can be negative and delta S can be positive, sir.
Exactly, right? So if you understand, if delta H is negative and your delta S is positive, irrespective of whatever the temperature is, the overall thing will always be negative because temperature cannot be negative. In the sense, yeah, temperature can be negative, but still, generally speaking, right? So at almost at all temperatures, right? So you can see that this process which is going to be spontaneous. So like this questions can be asked, okay? And there is other connections of delta G. You will be able to connect to something called an equilibrium constant. There are so many other things which is connected to this. Like you'll study in electrochemistry that this can be connected to the redox potentials of the system. So many things you will be able to do delta G. Okay, this is just an introduction for you. Okay, fine. So I think the next class, not in the next class, next chapter itself, right, you will be able to appreciate how this delta G values are going to help me thermodynamically. Okay, right, fine. And successfully we have completed your chapter. Thermodynamics chapter is completely over, right? So from next class we'll be starting with this chapter called as EQLM. As a short form, it's equilibrium. Okay, right? So we'll go for equilibrium, and with that your physical chemistry is over, right? That chapter is the last chapter where you're going to have problematic, I mean the numerical problems, right? But equilibrium you have to be very, very careful, right? It's a very, very interesting this thing, but there can be a lot of confusing stuff, so we'll take it slowly, right? Okay, what is the time? 7:55. No problem. So how like where are they in your school? So they're still in organic chemistry only?
No, sir, they finished that chapter and now they're taking P block classification.
They started P block, SN P block.
Yes, sir. They finished math. They finished S, sir, and
Oh,
now
they
they're
finished
doing
S.
P.
Okay. So I think they are a little ahead of us, right? They didn't complete gaseous state. Did they complete gaseous state?
Fifth chapter only, no, sir. No, they didn't do it, sir.
They didn't do that. So yeah, they are also 2 chapters away. We are 2 chapters here. Cool. Yeah. Anyways, but again, you can obviously look at the amount of stuff we learn in this class than what you learn in school. We are doing a good thing, right? We are learning a lot of stuff. Like not with respect to marks, right? You can see you should be able to appreciate. See, guys, according, like, the thing is, if you want to have the full benefit of attending my classes, let me tell you this, like, you should squeeze me. The more and more questions you ask me, the more and more things I'm going to let you know. That is how it is, because like this is like an encyclopedia, right? So the more and more you spend time with it, more and more you search for answers, right, the more and more you're going to get better at it, right? I would say please squeeze me, please utilize me properly, right? Because like I might feel that this might not be important. Obviously I'll tell you what is there required for your 11th class. But if at all you want to go beyond that, if you want to ask me some logical questions, you are always like welcome to ask those things. Even beyond the scope, beyond your syllabus, if you want to ask me something, you are always welcome, right? Cool. So I think we'll stop with this for today, people, right? So next class I'll be starting with equilibrium. That will be on Wednesday, right? So that will go for, so equilibrium is actually, I'll be able to divide into 2 parts. One is equilibrium, another one is, I mean, normal equilibrium and ionic equilibrium, right? So you will be studying about the pH. Like, you should just know the pH. We'll be calculating the pH in the next chapter, right? We'll do then you'll be like, for different acids, if you have HCl, H2SO4, CH3COOH, we are going to see methods, or we're going to see tricks to find out which acid is stronger acid, which acid is weaker acid. You just know by looking at it. You just know only the superficial layer of it, right? So we'll go in depth, right? So we'll see how is it done, right? There are a lot of other
Do we
stuff.
have numericals for this concept, sir? Second law.
Oh, this one, delta G.
Yes, sir. Do we have numericals?
Delta G, they will have, like, basically there will be a simple calculation only. They'll give you delta H value, temperature value, delta S value, ask you to calculate delta G. That's the only thing which can happen.
Okay, sir.
Right, but yeah, delta H, yes, you will get a lot of numericals. The entire thermochemistry part is very, very important.
Okay, sir.
Fine. Thank you, guys. We'll meet again.
Thank you, sir.
Yeah, thank you. Can you say the exact name of the topic you finished now, sir? No, it's second law of thermodynamics. That's the entire that only it is gonna come. Okay, Mithun. Okay, I hope you're there. Fine. Anyways, thank you. Third law and fourth law. Fourth law, we don't have fourth law. Third law, okay, fine. Third law we'll see tomorrow. It's just a statement and it's not important also, right? Fourth law of thermodynamics, I don't think, to my knowledge, I don't think there is anything called as fourth law. Okay, so we'll see third law. Third law is very simple. We can see that, not a big deal, right? Cool. Thank you, guys.